So today we're going to talk about vector addition. Um, so you note here, I have all my different colored pens. I'm just putting out there because I will be doing some color coding. So if you're the type of person that wants to follow along with that, you might want to grab a couple of different colors. So vector addition. Let's say we have two vectors, and I'll define them first both. A is equal to, and we'll use our friend from before, 5 meters east. And then we'll have another vector. I'm going to call it B, and we'll say that's 2 meters west. Okay, so a nice simple problem. And we'll do A plus B equals something. All right, so these vectors, these are actually both known as displacement vectors. And for full disclosure, this notation is, when we get to physics, not acceptable for this. We're using A and B, C, D, all these other notations because we don't know the proper variables for the types of vectors that we will do within the context of physics. When we learn those, we're going to learn different nomenclatures for what to call our vectors. But in just this abstract vectors unit, we're going to be using capital A, capital B, capital C, etc. Anyway, our first thing that we're looking at this, I think everyone can do this in their head. If I were to say to you, walk 5 meters east and then walk 2 meters west, and I say, where are you with respect to where you started? I think people would comfortably answer the question, I am 3 meters east of where I started. Great. So it seems like what I'm going to do here is going to be a bit of overkill for such a simple problem. But what I'm trying to do is highlight a methodology that is going to work irrespective of how many vectors we have and how difficult they are. So we're going to build up to a more complicated process using simpler steps. So we need to practice those simpler steps, even though we can all do this stuff in our heads. Okay? So just take that understanding. The first thing I want to do is I want to define a new thing here, and I'm going to call that vector R. And vector R is what is known as our resultant vector, right? It is the result of the addition of two or more vectors. Now, if you notice here, I'm going to leave a bunch of space under there because we're going to have a couple of different ways that we're going to describe the resultant vector. Okay, but that's just its base definition. So the way that we're going to do this for now is we're going to do this graphically. Once again, you may say this is overkill for such a simple problem. And to that, I would agree with you. Once again, we want to highlight new methodologies on simple problems so we can focus on the methodology and not the problem. Right? I think a lot of times people want to jump into the deep end and they don't understand cognitive science because cognitive science tells us oftentimes when you're trying to learn content at the same time as you're trying to learn skills, that you don't learn both of them at the same rate, right? That you may effectively learn one, but not the other, or conflate the two. So I'm really separating this out so that we can learn the skill and then we can deal with the content later. Okay, just a little bit on my philosophy there. So how are we going to do this vector addition? Well, the first thing we're going to do, and if you notice here, once again, I'm going to be big on process. So I'm going to be writing out our process here and we're doing the problem on a separate sheet of paper. So the first thing we're going to do is all the steps that we did the first time, which we want to set up our vector space. Okay, so what does that mean? Going over onto our other piece of paper, that means that I want to define my coordinate system. It makes sense to use the compass rose, given the types of vectors I have that have east and west as their directionality on them. Then I want to establish a scale. I'm going to use that same scale from before. It worked nice there. It still meets our standard of, all of my vectors above 2 centimeters. You know what? I'm going to even make it a little bigger. So here we go. To extend it out, 1 centimeter is equal to 0.5 meters. Therefore, I can be more precise about it. Not more accurate, more precise about it. Okay, so that's that. Next, I want to pick a logical starting point. Well, I know this thing is going to go both east and west, right? So I probably want to make sure then that if I do that 5 meter, that's going to be a 10 centimeter thing. So I want to make sure I'm going to stay on my page. So it looks like that is a good starting point. And I'm going to put in my horizontal guideline through my start point. There we go. Perfect. So I've set up my vector space appropriately. The next thing I'm going to want to do is draw the first vector to scale from the start point. Okay, so here we go. So I'm going to use, I'll use my blue pen for that. Great, so I'm going to draw vector A. We know that's going to be a 10 centimeter long vector. There we go. And that is vector A. Perfect. So there I have it. Draw the first vector to scale from the start point. Now, a couple little other vocabulary pieces. What you'll find in some books is that they've named the two parts of the vectors, the two endpoints of the vectors. This is called the tip of the vector. That's the tail of the vector. Okay, you may hear that, and I'll reference a notation or a way that people talk about vector addition a little bit later. All right, so now my next thing says, well, if we look at what literally addition says to do, it says do vector A and then do vector B. So now I want to draw the next vector. But here's the thing. Where do I start it? Because we know we can translate vectors around at will. So theoretically, I can start this thing at any point in the space that I want. But I have a specific goal in mind, which is to do a vector addition. So there's kind of two logical places that we can think about starting that. And that is starting the vector here and drawing it this way, or starting the vector here and drawing it this way. So either at the tail or the tip. Which do you think makes more sense to do if what I'm looking for is the addition of do one, then do the other? So hopefully what you said to yourself is, well, I want to start drawing the second vector where I ended the first one, right? Because we're going to think about this as like, what's a pirate treasure map, right? If you're given a pirate treasure map, walk this many paces this way, this many paces this way, etc. You want to walk out the first one. You don't want to go back to the start point and then walk from the start point. You want to go from where you are to follow the next direction. So here we go. Back to my process. Draw the next vector starting from the tip or arrow of the previous vector. And I cannot tell you how important this step is. This is the thing that people mess up. So I'm going to draw vector B now. I'm going to draw that in red. So vector B is 2 meters, so that's going to be 4 centimeters. Now I could draw it directly on top if I want to, or I can just like scooch it down a little bit if I'm worried about things overlapping. Being that I'm using pen here and not marker, it's not going to bleed. So I'm just going to do it directly on top. So 1, 2, 3, 4 centimeters. There we go. Okay. You can see then my B vector, right? So A, then B. All right. So we're not done yet because I need an answer now. So I'm going to skip step 4. And we're going to talk about what that is a little bit later. You might have seen some ways that I phrased this. I didn't say draw the second vector, but we'll see that in a second. So 5 is I want to draw the resultant vector. Now we know, based on this very simple problem, what we want is a 3-meter east vector. So it's going to be a 6-centimeter long vector that points to the east. And so if I look at this drawing, where is that? Well, hopefully you see that as this, because that section right there is 6 centimeters long. So what we're going to do is we're going to draw a vector that goes from the start point or tail of the first vector to the tip or arrow of the last vector. And that's what it means to draw the resultant. So I'm going to draw that in now. Apparently, I'm going to do that in pencil because my green marker is apparently out of ink. Lovely. Okay, I'm going to label that R. Now that's hard to see because everything is directly on top of each other. But just to draw a little sketch, if I wanted to draw this like this, just to make it clearer and more visually appealing, that's totally acceptable as well. I would just have to label this A, B, and R. All right. So there we go. So let's just write in how we drew the resultant vector from the start or tail of the first vector to the tip or end of the last vector. Now, we know what the answer is going to be, folks, but if you were doing a more complicated vector problem, I might not know what the answer is. So our last step here is to measure and report the answer. Okay, so how am I going to do that? Well, very simply, I'm literally going to measure. Just checking 6 centimeters. So here we go. I would say the magnitude of R is 6 centimeters, which we're going to put into scale as 3 meters. Okay, and then I would say vector R is equal to 3 meters. And then I'm going to look at the direction, and I can just say east and box it. Okay. And that is our vector addition process. Now, what is that fourth step? So if you notice here, draw the next vector starting from the tip of the previous and draw the resultant vector from the start of the first to the end of the last. We're going to have problems with more than 2 vectors. So what's step 4? Step 4 is repeat step 3 for each additional vector. And now we have a process for doing vector addition irrespective of the number of vectors that are offered. Okay, all right, cool. So let's go back to this. I want to ask a couple of questions. The next question I want to ask is, well, we did R is equal, oops, let me get that on the screen, A plus B. It's a logical question to want to ask. And that is R also equal to, so question mark, B plus A? So in the language of mathematics, what question am I asking? I'm asking, is vector addition, because it's a different type of addition than what you've been doing your entire life. You've been doing scalar addition your entire life, but is vector addition commutative? And we're just going to do a quick picture to see if it is. So what I'm going to do here is on the same area, I'm just going to float my start point up there. And we're going to draw vector B first and then vector A. So here we go. So vector B is for where the 2 meters west or 4 centimeters west. Okay, there we go. That's B. And then we're going to draw A, which is 10 centimeters long going east or to the right. So which are 5 centimeters east, 10. Boom. And hopefully you can see very clearly here that I am getting that same vector R. Cool. So I can cross this out and we can say A plus B is equal to B plus A, or that vector addition is commutative, which is really handy dandy. All right, great. So what you've noticed about our problems here is we've done the simplest type of problem that you can. That's because the given vectors all were along the same axis. So let's just take a moment and think about that. And so what I'm going to talk about here is vector addition of what are called of collinear vectors. Right? So let's say I have two vectors, A and B, but all I know is their magnitudes, 8 meters, and B is, I don't know, 6 meters. So the question I ask is, what is the maximum magnitude of the resultant vector? Meaning, I don't know the direction that these two vectors point. I don't know the direction of A and B. What's the maximum magnitude that you can have? So hopefully, should be pretty clear that the maximum magnitude of the resultant, so that would be symbolically magnitude of R max, that would be in this case 14 meters. So how do we get that? Well, we just added the two magnitudes together. Okay. So in what situation does that occur? Well, that occurs when the two vectors point in the same direction. All right. There's another way of expressing that. And there's another vocabulary piece that I want to bring up. So in this case, we might have vector A like this and vector B. So if I were to draw vectors A and B like this versus drawing them like this is how we drew them when we did our vector addition. This is drawing both vectors as if they started at the same point. We have words for that. This is drawing the vectors consecutively. And this is drawing the vectors concurrently. So concurrently or concurrent means the two vectors are drawn from the same start point. Consecutively, you draw the first vector and the second vector or the next vector starts at the tip of the first vector. So we saw that this for vector addition is how we're going to draw our vectors. There are times and places to draw our vectors concurrently. Let me give you a for instance. When we are talking about the forces that act on an object, we tend to draw all of those vectors concurrently because they're acting on the same thing. And that's just a way of visualizing it. So here we have two vectors pointing in the same direction. When drawn concurrently, what is the angle between those two vectors? So hopefully you're looking at this, say they point in the same direction, and we would see that there is a 0-degree angle between those two vectors. And that's a way of talking about it. And there's a word that means that there's a 0-degree angle between two parallel, or rather between two rays, and I just gave it away. We would say those two vectors are parallel. Okay, cool. What would be the minimum magnitude of the resultant? So R min. I think we can look at that and see pretty obviously it's going to be 2 meters. And in this case, it's just the magnitude of the bigger one minus the magnitude of the smaller one is going to get us that. Okay. So what would be true about the two vectors that would give the minimum possible resultant? I think we would understand then those two vectors point in opposite directions. Now, let's just talk about that for a second. Opposite, right? Opposite is not the same thing necessarily as different. We want to say the word opposite, meaning if one vector is like this, the other vector is like this. Exactly opposite. Because different just means if one's like this, the other could be like this or any other direction, just that's not the same. So it is, all opposites are different, but not all differents are opposite. And I do mean the word opposite in this case. So when drawn concurrently, and there we go, what's the angle between these two vectors? Hopefully this diagram helps you see that the angle is 180 degrees. So when drawn concurrently, there is a 180-degree angle between those two vectors. Okay. And one last note for this video. If we have those two vectors in exactly opposite directions, what are those two vectors with respect to one another? And it's very tempting to say parallel, but that's not true because these are not lines, they are rays, right? You think of two parallel lines, yeah, so since lines have no directionality, there is only parallel. But with rays, it is possible to be lining up in the same direction with the arrows pointing in the same direction. And oppositely, there is a word for that, and that word is anti-parallel. And it's probably not a word that you talked about in coordinate geometry when you took geometry, because you don't really do the geometry of rays all that often in your abstract math classes. Okay, so there we go. We now have a way of doing the vector addition of collinear vectors. And we're going to see that that same process that we came out of for doing collinear vectors is going to be the same as if our vectors are no longer along the straight line, right? So what's going to be the next easiest type of orientation to deal with, hope you figured out, is if our vectors are perpendicular to each other. So not zero angle between, not 180, but 90. And then we'll talk about, well, what do we do when it's somewhere that's not perpendicular or parallel or anti-parallel, somewhere in between. And so those are the next two videos. So next we're going to do perpendicular vectors, and then we'll go on to vectors at any angles. And from there, we're just going to find out that all of this stuff is just the same. The method is the same. The only thing that's different is the detail level.